Hello, welcome to this lecture series on electronic properties of materials. This is lecture number 6. In this lecture, I am going to discuss a very important and very famous law called WIEDEMANN-FRANZ law. Before going to see the actual statement of WIEDEMANN-FRANZ law, I'll give some information about materials. See, in general, materials which are good conductors of electricity, good electrical conductors, materials which are good electrical conductor can also behave as good thermal conductors in general. Okay, in general, materials which are good electrical conductors can also behave as good thermal conductors. Yes, this was observed in metals. Okay, so in metals, in most metals, right, metals not only have high electrical conductivity, okay, high value of electrical conductivity, they also have high value of thermal conductivity, right? This is a well known one. Experimentally scientists have found the values of sigma and k for different metals, and it was said that metals in general, they have high electrical conductivity as well as thermal conductivity. Okay, now in metals, I have already told you, in metals the thermal conductivity, okay, this is thermal conductivity which is very high in the case of metals. Clear? In metals we have two different ways of getting the thermal conductivity in metals. One due to lattice vibration, let me represent this as K lattice, and another one due to electronic movement or the movement of the free electron. Let me represent that as electronic contribution to thermal conductivity. Okay, so in thermal conductivity, in the case of metal, we have two different thermal conductivities: lattice thermal conductivity and electronic contribution to thermal conductivity. Clear? The two scientists, Wiedemann and Franz, they observed that, let me write the next page, they did they measured quantitatively, okay, the electronic contribution to thermal conductivity and electrical conductivity of many metals, okay, and they gave this law. Listen, at a given temperature, okay, what they did, they took a metal and they measured the electronic contribution to thermal conductivity and the electrical conductivity of the material at the same temperature T, and they carried out this for many metals. Okay, the same procedure is repeated. The same procedure is repeated with many metals. Okay, you keep the temperature same, right? Measure the electronic contribution to thermal conductivity and the electrical conductivity of the metal, and they found that this ratio, that is electronic contribution to thermal conductivity to the electrical conductivity of the material, this ratio is directly proportional to absolute temperature of the material. This is what we call as Wiedemann-Franz law. So what is Wiedemann-Franz law? Very simple. It is the ratio. See this ratio. What is this ratio? Electronic contribution to thermal conductivity to the electrical conductivity of metals, okay, is directly proportional to absolute temperature of the temperature at which these two quantities are measured. Clear? This formula is applicable for metals, right? And if I equate this thermal conductivity over electrical conductivity, if I equate this, we should introduce a constant. Yes, you'll get a constant times temperature. If I bring this temperature this side, so we can find out the constant. We can find out this constant. Okay, this the value of the constant was found by Lorentz through quantum mechanical work. He found the value. The value is, let me write here, that is this contribution of electronic contribution to thermal conductivity divided by electrical conductivity into temperature. This is a constant, and this constant is equal to pi square by 3 into Boltzmann constant Kb by E the whole square. He found this constant by using quantum mechanical ideas, okay, which we are going to discuss once we complete the classical theory of thermal conductivity. Okay, and this quantity is equal to 2.445 into 10 to the power minus 8. Okay, you'll get watt ohm per Kelvin square. This is the unit for this quantity. It's called, and this quantity is what we call as Lorentz number. Lorentz number. Okay, listen, Lorentz found this using quantum mechanical ideas, and experimental results also, okay, predict this value, right, almost correctly for many metals. Okay, for many metals the experimental value of the constant and this constant are almost same. Okay, yeah, so this is Lorentz number. Now what we are going to do in the next lecture is that we are going to use the Drude theory, okay, and based on that we are going to get the expression for thermal conductivity, electronic contribution to thermal conductivity, and we are going to calculate this ratio. We are going to see whether we get constant or not. Okay, if I get constant, yes, the Drude model support, or the Drude model follow the WIEDEMANN-FRANZ law. Okay, and we are also going to compare whether we get this value or not. Okay, yeah, so this is what we are going to do in the next class. Okay, so now before finishing, let me just give the formal statement of WIEDEMANN-FRANZ law. So what is WIEDEMANN-FRANZ law? The ratio, that is electronic contribution to thermal conductivity to the electrical conductivity, right, this ratio is directly proportional to absolute temperature of the material at which these two quantities are measured. Okay, this is what we call as WIEDEMANN-FRANZ law. This law is applicable for metals. Clear? And in WIEDEMANN-FRANZ law, I have told you this quantity, if you bring temperature this side, you'll get this. This is actually a constant. This constant was found through quantum mechanical methods by Lorentz, and that number is 2.445 into 10 power minus 8. Okay, and experimentally people have found this value, and that value is almost matches with this value. Clear? But here it is very important, this number, okay, it is a constant for almost all metals. We get same number, same value of constant for all the metals, but this is correct only at a high temperature, only at a high temperature or room temperature. At high temperature, yes, it is good, but at low temperature, the value changes. Okay, Why the value changes at low temperature, that could not be explained. That's what we are going to discuss, okay, in the forthcoming lectures. Clear? Yeah, I stop here. We'll continue the Drude theory of Drude explanation for thermal conductivity of metals, okay, in the next class. Right, I stop here. Thank you for listening.